Namaste. Welcome to the course on sampling, p-value, power and effect size and reporting results. Let me give you some context. While reporting results, researchers generally stop with p-value significance. Should the researcher go beyond the p-value? In fact, what is the history of p-value? What are the limitations of p-value? And what reporting is expected by American Psychology Association? We need to think these areas before entering into discussion on limitation of p-value and other related areas. The following are the questions we would like to answer. What are the important outcomes to be reported in the human resources research? Is statistical significance is equal to practical significance? Why p-values are criticized by the researchers? Will history of statistical significance offer some clarity for us? What is inflated error rates, statistical power, effect sizes? How to use G-power for testing statistical significance? How should a human resources professional will report his or her finding? Let me start with a very significant paper by three well-known authors who have examined research across 60 years on statistical significance. I quote from them, "Statistical significance is, we argue, a diversion from proper objects of scientific study. Significance reduced to its narrow and statistical meaning, only p less than 0.05, has little to do with the defensible notion of scientific inference. It is arbitrary, mechanical, illogic, though currently sanctioned by science and bureaucracies of reproduction, is causing a loss of jobs, justice, profit, and even life." These statements are very strong words, but coming from well-respected authors. And these papers, in addition to the reporting done in various journals, have given rise to American Psychology Association coming up with the following statement regarding reporting of results. For the readers to appreciate the magnitude or importance of a study's finding, it is almost always necessary to include some measure of effect size in the result section. Whenever possible, provide a confidence interval for each effect size reported to indicate the precision of estimate of the effect size. The effect sizes may be expressed in the original units and are often most easily understood when reported in original units. The general principle to be followed, however, is to provide the reader with enough information to assess the magnitude of observed effect. What this entire two reports, the research report, Cult of Statistical Significance, and American Psychology Association recommendation indicate for us. In most of our research, generally researchers stop with reporting p-value, and they say that if it is less than 0.05 or it is greater than 0.05. If it is less than 0.05, we reject the null hypothesis. But what exactly is this 0.05? And the authors I have cited, they felt that it is doing a lot of injustice to scientific endeavor. Therefore, in your research, when you are reporting, you will be reporting the p-value. We will just see all those areas during the course of our discussion. Let me start with history of significance testing. When this entire significant testing has come into existence, was it there in the 18th century, in the 17th century, or is it a 20th century finding? Or what exactly we mean by significant testing? Let us go to some historical aspects and then understand p-value, then effect size, then how to get both these aspects into our research and report our research findings. We all know Florence Nightingale, and she is an English social reformer and statistician and data visualizer in modern terms. She is known for founding the nursing profession. However, he is an extraordinary statistician. He came out with vital statistics with the help of other statisticians, and you can see here the data visualizing capability of Florence Nightingale. She has given the circular histogram, and today we follow the same data visualization model in many of the data visualization areas that we look into. And during Cimmerian War, he has given the death of various soldiers and related areas in the following diagram. Now, this has happened during 18th century and at the beginning of 19th century. And one more interesting thing has happened. Ronald Fisher, as you all know, introduced the p-value, level of significance to evaluate evidences. There is something in 1920s it has happened that a woman has claimed that she can find the difference if tea is poured first in milk or milk is poured in the tea. Initially, it appears very trivial. No, it has given rise to one of the finest scientific findings by Fisher. Now, let us sit back and think about this lady or a woman claiming that she can, by tasting, she can find the difference. If milk is poured into tea, the taste will be different. If tea is poured into milk, the taste will be different. And she says she can clearly identify these two aspects with, she has the ability. Now, Fisher started thinking, how should we test her? Can we give her a large number of, how large number of teacups we have to give her, so that we come out in confidence and say that, reject her thesis or her claim that she has an ability to taste the tea and find the difference. Or if she is successful she is successful in predicting the tea and the milk phenomena, how we have to really establish this? Please remember, many of the things in the world starts with very small kinds of these kind of incidents, and then scientists observe those things and then come out with a theories which has revolutionized science. Now, the tea experiment. The woman claimed to be able to find by tasting whether a cup of tea with milk had the tea poured first or the milk poured first. An experiment was performed and 8 teas are prepared and given to her in random order to identify. 4 had the milk poured first and 4 had the tea poured first. But they are given in a random order. She doesn't know what exactly is the combination of tea and milk. The lady tasted each one and gave her opinion. If she guessed all 4 correctly, the probability of happening the event is 1 by 70. How did we come to the conclusion to that 1 in 70 chance? Let us see the mathematical calculation. This I have taken from the Wikipedia. The test statistic was a simple count of the number of successes in selecting the 4 cups. The number of cups of the given type successfully selected, the distribution of possible number of successes, assuming the null hypothesis was true, was computed using the number of permutations using combination formula with n is equal to 8 total cups and k is equal to 4 cups chosen. Therefore, T testing distribution assuming the null hypothesis. Now, first successful count 0. Now, the permutation of selecting 0 is 1. The number of permutation of selecting 1 is 16, 2 is 36, 3 is 16 and 4 all correct is 1. Therefore, it starts from all not able to find to all she is able to find, totaling to 70 different permutations. This 70 different permutations, possible permutations, has given rise to the theory given by Fisher. If she could do it find all the successfully, she could find that the probability of that happening is very low. Therefore, even if she loses 3, the probability of happening of that event is 0.22. I want you to calculate that probability. How that becomes, if there are only 3 cups she could choose and 1 she could not, still she will not be able to prove her that she got the capability. In reality, he proved and she proved that she had the ability. We had the null hypothesis rejected and accepted the alternate hypothesis that she has the ability to find the taste. But still, how the null hypothesis have been created, how alternate hypotheses are created, what exactly is the mechanism that goes behind this entire process, we will discuss little after studying one important area by Neyman and Pearson's approach. Neyman and Pearson approached the same issue from a different perspective. Now, they believed that scientific statements should be split into hypotheses that may be tested. They call them as experimental hypothesis or alternate hypothesis and null hypothesis. That is, researchers what they wanted to prove becomes an experimental hypothesis and the exact opposite is null hypothesis. Therefore, they are mutually exclusive statements. Either one can be true. You cannot have both truths. The hypothesis of prediction from theory will generally have an effect. They are the first people to propose the importance of effect. When we design experimental hypothesis or alternative hypothesis, why there is a need for null hypothesis? This is a very important question. When we can design the experimental hypothesis, we will prove or disapprove it. Why should we have an alternate hypothesis in the form of null hypothesis? Please do remember, we will not be able to prove the alternative hypothesis by statistics. What we do instead is try to reject the null hypothesis so that we have support, not causation. Please remember, rejecting null hypothesis is not proving alternate hypothesis or causing. We have enough evidence or support for our alternate hypothesis. Therefore, the major takeaway from Neyman and Pearson approach is the effect and creation of alternate hypothesis in the form of null hypothesis. Now, they also came out with type 1 error and type 2 error. What is type 1 error? We have already seen in the sample size determination. We conclude that there is effect when there is no effect. That is a type 1 error. We conclude that there is an effect, but there is no effect in real world. Therefore, probability of this error is generally set to 0.05. This we call it as p-value. Type 2 error is we conclude that there is no effect when there is effect in the real world. Please do remember, the type 1 error and type 2 error are exactly opposite. We conclude that there is effect when there is no effect, and here we conclude that there is no effect when there is effect. Enough literature have been developed on type 1 and type 2 error, and you read about it across the textbooks. But one important thing is, can we address both these things? Yes, but we cannot address them in isolation. If we decrease the probability of type 1 error, automatically type 2 error goes up. You will find there is a trade-off between both the errors. We will see more of this in this. When type 1 error is intuitive and to a large extent appreciated by the researchers, type 2 error requires more reporting. That is what is given by American Psychological Association. It is important effects happening in the real world should not be missed, and it is known as beta level. Cohen 1988 suggested the maximum acceptable probability for this error to be 0.20. Translated into practical terms, out of 100 samples, we will not be able to detect 20 samples even if the effect exists. Neyman-Pearson identification of errors. While type 1 error is intuitive and to a large extent appreciated by researchers, type 2 error requires more reporting. It is important. Effects happening in the real world should not be missed, and it is known as beta level. Cohen 1988 suggested the maximum acceptable probability for this error to be 0.20. Translated into practical terms, out of 100 samples, we will not be able to detect 20 samples even if the effect exists. That means 80%, that is 1 minus beta level, 80% we are confident that we will be able to find the effects, 20% of the cases we will be missing. Now, some of the limitations of p-value, let us think. Is failing to reject the null hypothesis is equal to accepting null hypothesis. Therefore, we have a null hypothesis and we generally reject or accept the null hypothesis. If the value is less than 0.05, we will reject the null hypothesis. Soon we will find with a small experiment what exactly this process of rejecting or accepting null hypothesis happens. But in here we just try to find, is failing to reject null hypothesis is equal to accepting the null hypothesis. Failing to reject the null hypothesis is not equal to accepting the null hypothesis. The null hypothesis is never accepted, and failing to find an effect is not the same thing as showing that there is no effect. It is incorrect to claim evidence of no treatment effect or no difference if we fail to reject the null hypothesis. We may say that there is inconclusive results. Let me explain further. Now there are two theories we have. One is theory given by Fisher, another given by Neyman and Pearson. There is a lot of debate for 70 years that one theory is better than the other, or there was a lot of narcissistic competition between both the researchers. But there exists a difference between both the approaches. However, they are complementary. Both approaches can be used together for research. That is how we got into the way of doing null hypothesis testing. You can see a good article given by Neyman. It will give you a good understanding of the compatibility of both the theories. This we call it as null hypothesis significant testing. What we do here? We assume that null hypothesis is true. There is no effect. We fit the data to an experimental results or a model to represent alternate hypothesis, and how well it fits is the most important thing. We find the p-value of getting the model if the null hypothesis is true. If the probability is very small, such as 0.05 or less, then we gain confidence in the alternate or experimental hypothesis. Now, this is the process of null hypothesis significance testing. We assume that the null hypothesis is true, we fit the data to an experimental result, then we find the p-value of getting the model. If the null hypothesis is true, then if the probability is very small, such as 0.05 or less, we gain confidence in the alternate hypothesis and then say that we reject the null hypothesis. This we call it as null hypothesis significance testing, or NHST. Now, what is significance testing? Now, the question that has come from Fisher from the t-testing experiment, it is still bothering us. It is a process of comparing the p-value obtained from sample data to a predetermined level of significance decided by the researcher. That means the researcher decides beforehand, or we call the word a priori, a level, and he says that out of X number of trials, I can maximum fail in some percentage of that. Now, how does it translate into practical terms? The level of significance is the probability of committing type 1 error. This we define as finding evidence in the sample or difference when there is no evidence or difference. Therefore, type 1 error is finding evidence in the sample what in reality it has no existence. Now, the conventional level of significance used in most of the studies is 0.05, which corresponds to rejecting the null hypothesis incorrectly in a crop approximately 1 out of every 20 experiments. This is what has been given by Fisher. Fisher felt that 1 out of every 20 experiments can take this particular risk based on sampling. The p-value does not give information on hypothesis being true or false. The p-value gives the probability of observing the sample data or something more extreme, assuming the null hypothesis is true. What is extreme? In fact, what exactly is this null hypothesis is true? And let us do an experiment so that we will understand it more better. Now we will do a coin experiment. Now please we take a coin and we assume that the coin will give head or tail with equal probability if it is a fair coin. For example, I take a coin and toss the coin, then I have equal probability of getting head or tail. I am having this coin and I have no ability to find it is a fair coin or a biased coin. Biased coin means this coin may give a heads more number of times or tails more number of times than 50%. Fair enough? Therefore, I have a coin. I want to test whether it is a fair coin or not fair coin. Therefore, let us test the hypothesis. The null hypothesis is the coin is fair. Therefore, I am assuming that this is correct. Now, let us toss the coin. I get head first. Therefore, the probability of getting head is half. I have no evidence to suspect the coin. Good, I have got a head. So, I go ahead with the null hypothesis. Now, then I toss the coin. This time I again get an head. The probability of this event is half into half is 1/4. It's okay, it can always happen. Therefore, in the second time, the probability of happening again head is 1/4 or 0.25. If I toss the coin again, I get a head. Third time, the probability of happening of this event is 0.125 or 1/8. Slowly I started suspecting whether I have made a right judgment. And if I toss the coin again, the probability of event is 1/16, that is equal to 0.0625. I started suspecting my null hypothesis. Now, if I toss the coin, first time half, second time third, fourth, fifth time, the probability, again I get a head, the probability of happening of the event is 0.03125, very low probability. Therefore, after the fourth toss, and by the time I get into the fifth toss, there is a little evidence to support the null hypothesis is true. This is considered as an extreme and null hypothesis is rejected. Therefore, the null hypothesis, we assumed it to be true and we started fitting the data. Therefore, slowly when I started fitting the data, after fifth toss, I got a probability of happening of that event 0.03125. Then I say, sorry, I may not accept the null hypothesis. I think this coin experiment is it's not a sophisticated mathematical way of proving, but still it proves the point that how null hypothesis is created and how exactly it has been rejected in this particular case. Now, the limitations of p-value significance. Therefore, we have identified p-value, but we say that we reject the null hypothesis. But is there a limitations for the p-value? Yes. Now, the level of significance p less than 0.05 is a subjective quantity arrived by the researcher and may differ from other researchers. Probably I may select 0.01. This suggests clearly that it is a subjective procedure. Therefore, to believe that a significant test is an objective measure of scientific evidence may not be correct. What happens if the p-values are 0.03 or 0.0005 for same type of experiment conducted by two different researchers? Now, in both the cases, we will be rejecting the null hypothesis. But do you think that there is some kind of a difference between these two? No, in the case of scientific research. Both researchers A as well as B inferences are treated the same. No much significance in the p-value of 0.03. The p-value less than the predetermined value of significance 0.05, which is predetermined by the researchers. Therefore, both the researchers conclude that the null hypothesis is rejected. They will not go further. Now, p-value and sample size. This is the most important thing why we have included this particular lecture. The p-value and statistical significance are influenced by sample size. If the sample size is very large, the p-value necessarily will be very small, as increasingly large sample sizes yield decreasingly smaller p-value. Thus, a large sample size lead to a statistically significant results regardless of scientific importance. This is very important. If a small sample is not able to prove, if someone can increase the sample size to that an extent, probably he can prove a statistically insignificant results as significant. Therefore, a statistically significant effect based on small sample is more important than statistically significant effect based on large sample. Can we conclude like this? We may not. Inflated error rates or multiple comparisons. Let us imagine we use the 0.05 level of significance in research. In most of the HR researchers, we will be using this, and this is only for one test. For example, if you are administering two tests or two instruments, if you conduct two tests, the overall probability of no type 1 error will be 0.95 multiplied by 0.95 is equal to 0.9025. Then the probability of at least one type of error goes by 9%. From 5%, it goes to 9.75%. Therefore, if you use 3 tests, 4 tests, this goes on getting multiplied. In fact, it becomes 0.95 multiplied by to the power of n. Therefore, if you use 5 tests, probably the error rate will go up. Thus, across the tests, the type 1 error increases, or it is known as experiment-wise error rate, or sometimes referred as family-wise error rate. The general formula for the same is given by 1 minus 0.95 whole to the power of n. This may be controlled by using Born-Perroni correction. P critical value is equal to alpha divided by k, where k is the number of comparisons. As you can see, it reduces the statistical power, because from 0.95 you are imagining only for one test, it gets multiplied and you will find that it gets reduced. It is reducing your statistical power. Important remarks. There are two variations that are there in any experiment. One is systematic variation. if the variation that can be explained by the model. We call it as systematic variation. Now, you are taking a model, there is a null hypothesis, alternate hypothesis, we try to accept or reject the null hypothesis. In the process, we build evidence for our alternate hypothesis. Therefore, this building of support for your alternate hypothesis comes from ability to explain the systematic variation. There is another variation known as unsystematic variation, is one thing that cannot be explained by the model we have designed or the experiment. This is the variation is not attributable to the effect we are experimenting or how we use it for testing. Therefore, when you are using t-test or chi-square test or f-test, you have a particular threshold value, and this particular threshold value, if it exceeds the threshold value, then we say that yes, there is evidence. Now let us see. Very important remark. In effect, what we are finding in the test statistic, variance explained by the model divided by the variance not explained by the model. Therefore, it is effect divided by the error, or noise. We are taking signal to noise ratio. This ratio of effect to error or signal to noise is called the test statistic, and TEF, chi-square, or signal to noise ratios. If the effect to error ratio is 1 or more, the effect is more than error, but need not be significant. It has to be significant. We have started our entire discussion with trying to find out the importance of or cult of p-value significance, as some scientists have told, and try to find there is a need for power, need for giving effect size and reporting the results. We will follow up this particular lecture with another lecture on G power, in which we will be discussing on statistical power and using a software known as G power software to make your entire analysis easy, so that you can concentrate on your domain expertise rather than going into the statistical analytical aspects, which can be easily done with the help of a freely available software. We will see you in the power analysis lecture. Thank you very much. Please do give your comments and use discussion forum to help us to serve you better. Thank you. Namaste.